Hey, what's going on, folks? It's Mike here, and welcome back to our modern OpenGL series. So in this lesson, I want to go ahead and talk about the part of the pipeline that happens after you specify your vertices. In the previous lesson, we talked about the vertex array object and the vertex buffer object. The vertex buffer object being our actual raw data, the x, y, and z positions of a vertex, for instance, and the vertex array object telling us that we have an x, y, and z, or position data, for some data that we might want to lay out. That vertex array object might also have different layouts depending on what's in our vertex buffer object, things like texture coordinates, colors, normals, and so on. But what happens after we actually specify our vertices? Well, for that, we're going to have to actually look at our graphics pipeline. So let's actually take another look at our graphics pipeline here. Now keep in mind that this pipeline is what goes on the GPU. So this is the actual rendering pipeline. I've grabbed this figure from the Chronos Wikipedia page if you'd like to read more about it. So the vertex specification part, if you recall, this was our VAOs and our VBOs. Okay, so essentially what we're doing at this stage is specifying some vertices. So you could imagine in our CPU side, that is our C++ file, we have something like this. Maybe a standard vector of floats, and I just call it, vertices, and we specify a bunch of x, y, and z positions in this initializer list. Okay, and then we ship things over to a vertex buffer object using commands like glBufferData, generating those buffers, and so on, and then setting the attributes with a vertex array object. So that's essentially what happens and what we talked about in the previous lesson when we're specifying our vertex specification. But at this point, we don't have a graphics pipeline in. So we need to have the rest of this process. And I'm going to draw special attention to the Vertex Shader here and the Fragment Shader, because those are the two pieces that we absolutely must have. These other stages here, tessellation, geometry, or compute shaders, or these types of things are completely optional. But we must have a way to process or position our vertices in the Vertex Shader, and then finally, after determining which pixels are rasterized in the rasterization step, how to shade them in the Fragment Shader. Now this is very cool because we have the power to program how this actually happens. This is what makes modern OpenGL. So let's go ahead and take a look at the Vertex Shader first. And I'll admit that this is a little bit weird what I'm going to show you, but again, let me just explain and it'll all make sense soon. So what I've pasted in here is an example of a Vertex Shader. And this is probably one of the more simple vertex shaders that you can have. We specify things like the version and, well, the input, which we'll have to talk about here. And then we have some other things that look familiar if you've done any amount of C or C++ programming, which hopefully you have. If not, check out my other series. But we have our main here, which is the entry point into our program. So the idea is, again, we always start from the main here. And in this vertex shader, this is going to be our sort of hello world vertex shader. We have a singular built-in function here. Now, vertex shaders and fragment shaders and the other shaders have built-in functions. They're usually indicated with a GL underscore, and that's how you'll know they're built-in. They're variables that we haven't defined anywhere else. But what is this vertex shader doing? Well, again, it's a pipeline that we have here on the left side of the screen. So we're taking in position data. Where is this position data? Well, that's part of one of our vertex buffer objects. And there's different ways that we're going to communicate if we have color information or position information or other things. But for now, we just have X, Y, and Z positions and a W coordinate, which we'll have to talk about later. But that's all that we're bringing in right now. And then the idea is per vertex in any triangle. So if I have a triangle here with 3 vertices, I need to position it so this vertex shader runs once for this vertex, once for the other one, and once for the other one in some non-deterministic order. So that's the idea, and this is what our vertex shader is doing. And again, we have through some data structure here, which is just a vec_for, which is just some simple struct with an x, y, z, and a w position, that we're retrieving this information and just positioning it accordingly. Now we could do things here like add +1 or plus some sign function and then take in some other input like the time and kind of move around our vertices if we want. This is what's powerful about the Vertex Shader. We do all of our transformations here by positioning our vertex. So once we've actually run our vertex shader, the position of our individual triangles that we're rendering, if we're working with a triangle primitive, has been set. And then now we can take this information, again from our vertex shader pipeline, and then move down our pipeline through the other stages. Again, we might have some optional stages like tessellation, geometry shaders, the vertex post-processing, which puts together and starts assembling things in the primitive assembly. And then ultimately, once we have our triangles here, they go through this rasterization step, which says, hey, these are the triangles that will need to get filled in. And then finally, we get to our fragment shader, which is the next part that I want to talk about here. So the fragment shader, again, is a separate program here. We can see that it is, again, down here, and our vertex shader is up here. And what this means is we have to, again, have this second program that's going to get compiled and executed on the GPU once per fragment. Again, you can think about that as once per pixel if you'd like, but it's really once per fragment. So we'll see a similar indication of what OpenGL version we're using, 4.1 for the most part of this series. We're going to see this out variable, vec4, which is familiar from before from our vertex shader, and then this idea of color. Well, what's really going on here, and if we start looking at the main function, is we just have one color variable. And again, this is going to be new if you've only done C++ or C programming, but this idea of an out specifier, something that's going to move out to the next stage of the pipeline. We saw in our vertex shader that we had something coming in or to the next stage of the pipeline, but this time our fragment shader, which is really the last stage here, just sends out one piece of information, and that's the final color of the fragment, or again, the pixel, if you want to think about it that way, that we are filling in. Okay, so that's the idea that I can determine here what that color is going to be using an R, G, B, and then an alpha value for how opaque that pixel is going to be, if we want transparency, for instance. So that's how a fragment shader works. It just determines the final color. But since it's running per pixel, we can do some very powerful things like per pixel lighting calculations, which we'll look at later in the series when we have a lighting model. So I want to go ahead and show you what this is going to look like in the code that we are actually going to write in this series. And in a sense, what I've put up here is going to be a little bit weird. So if you go ahead and just take a moment to look at this, you're going to notice that, well, it's the same exact code here. Here's our vertex shader. Here's our fragment shader. The one thing that's going to be different, and that's a little bit weird to folks who are coming into OpenGL, is that this is just a string here. It's a C++ string, and you can see I've put in end lines and all these things, some of them necessary, some of them not necessary, and then the actual same code that we had. Well, what OpenGL is going to do is use OpenGL commands to build individual shader objects. So we're going to get a shader object for our vertex shader. Let me highlight it here. And then another shader object for our fragment shader. And then what's ultimately going to happen is that we'll run some commands like gl compile shader. We'll do the same for our fragment shader. We'll compile it here, gl compile, etc. And then we will link these together in a link step and get a final, I'm just going to call it program object. Let me give myself a little bit of room here. Program object that represents the actual pipeline here that you see on the far left. So we'll take, again, our vertex source, our fragment source, and we can have any number of these, but we're just going to assemble one pipeline for now that determines how we render our vertex data specified in the vertex specification. So I think the tricky part here, or the part that, again, beginners sort of get tripped up on, is this idea that within our actual C++ code, we're going to be calling functions that compile this source code. So yes, that does mean you will get some syntax errors and have to fix them. I'll talk a little bit about the workflow later, but in a way, this is kind of a cool or way to work. But this makes sense because when we're running our CPU program, we actually have to compile this source that's going to be sent to our GPU, just like other GPU instructions that we would ultimately do. So we need to compile at runtime this source code, send it to the GPU, and then we can execute on our triangles as we need. Ultimately, once we've put all this together, we'll do something like gl draw arrays, or GeoDraw elements, which are draw calls, which will execute this entire pipeline using the graphics Vertex Shader and Fragment Shader that we've specified. All right, folks, I hope that gives you some more intuition about this idea of shaders, where they belong, and where they look like. Shaders can actually be quite simple in the sense of what we've seen here. They're just a few lines of code. Sometimes they do grow more, but that's often once we start adding lighting and multi-texturing and other cool features that you might want to implement, these things that you see in the latest and greatest games that you have so much fun playing. All right, folks, I'm going to go ahead and end it here, and then we'll dive into actually doing some more OpenGL shortly. So I hope you're enjoying this series. I hope you'll leave a like or a thumbs up down below so I know. And as always, make sure to subscribe so you don't miss the latest lessons. Thanks for your time, folks, and we'll see you in the next one.